Hello guys, welcome once more to another video in this YouTube channel. So in this video of today, we are going to be looking at this very complicated topic, as many students and teachers say. The topic is rotational dynamics. So it is a further maths mechanics topic, and this topic is actually, I don't know if it is as complicated as both teachers and students talk about it, but I believe that at the end of this video you're going to see how to always analyze problems under this topic whenever they are given to you. So stay tuned for more videos on rotational dynamics. In this very channel we have, I think, 3 videos on rotational dynamics. We have 2 videos that were explaining some basic concepts, and 1 video which was solving a past GC question, that is 2019. So in this video, this is a tutorial question that was sent to me by a colleague, and it is from the Northwest Regional Mock of 2023 for the maths paper 3. I think it was question 6. Okay, so like I said, stay tuned to more videos on rotational dynamics, and if you're a teacher, I believe at the end of this video you'll be able to grab some important concepts that will help you whenever you're explaining or teaching this topic with your students. If you're a student as well, you're going to grab some important concepts that maybe will help you to explain it to your classmates or to whosoever you meet who needs help in the topic. Make sure you share the video with your friends, encourage your friends and teachers to subscribe to the channel and stay updated. So let us begin with what we have for today, and the question is divided into 3 parts. Okay, so the question reads: a uniform rod of mass 4m and length 2a has a particle of mass 2m attached to the NB. The system is free to rotate in a vertical plane about a small horizontal axis through A. Okay, show that the moment of inertia of the system about this axis is I equal to 40 on 3 ma squared. The rod is released from rest when AB is horizontal. Show that when AB makes an angle of theta with the horizontal, this happens, and then find the components perpendicular to AB of the reaction force exerted at the axis. So whenever you're faced with questions on this topic, the very first thing to do is that you sketch your diagram to see what is happening. So we have a rod AB that have given us the mass of the rod, that have given us the length of the rod, and then we have another particle whose mass is 2m, and this particle is attached to one end of the rod, the NB. Now the system is free to rotate in a vertical plane about a smooth horizontal axis through A. Okay, so if the system is rotating about a vertical plane through, if it is free to rotate in a vertical plane about a smooth horizontal axis, it means that initially the system was, that the rod was in a vertical position. Okay, so we have our rod in a vertical position, and then we have let's just say here is a rod which is in a vertical position. Now we have, let's just label the point A as one end of the rod, and then the point B also the other end of the rod. Now it is free to rotate in a vertical plane about a smooth horizontal axis passing through A. Okay, so we have our horizontal axis passing through A. There is a horizontal axis passing through A. So we can just say the axis is the axis delta, for example. Now that is A there, and then we have the other end of the rod is B, but at this other end of the rod we have a mass of 2m. So we have a mass of 2m which is placed there. So here we have a mass of 2m, so this is B. Now at the other end, like I said, a mass of 2m is placed there, and then we need to show something, that the moment of inertia of our system, so let's say the mass is 2m. Let's just indicate a particle. Let's just say that here is a mass of 2m. Okay, let's do something like this. So we have this, and we have 2m here. Alright, so this is what we have. So like I said, let us indicate that that horizontal axis is the axis delta. The body, this system is free to rotate in a vertical plane about a small horizontal axis. So you see it is rotating like this, left, right, for example, like something like simple harmonic motion or a simple pendulum. That's just an example. Okay, alright, so we need to show something. We need to show that the moment of inertia of this system about the axis delta here is 40 ma, 40 on 3 ma squared. So let's just let the moment of inertia of the system be I. Okay, now the moment of inertia of the system about the axis, let the moment of inertia of the system about the axis delta be I. Now it means that let's be specific, be I delta. Okay, so it is I delta. Let's just be specific to show that it is about the axis delta. So to get this, we just need to sum the moment of inertia of this system, that's the moment of inertia of the various bodies in the system, so about this axis. So the moment of inertia of the system about the axis delta is the moment of inertia of the rod about that axis plus the moment of inertia of our point mass about that axis. Now all we are left to do is to find the moment of inertia of the rod about the axis and the moment of inertia of our mass about the axis. So let us begin with the moment of inertia of the mass about the axis. So the moment of inertia of the mass, by the definition, is simply the mass times the square of the distance separating the mass and the axis. Okay, the mass of the particle is 2m, and then the distance separating the particle and the body is simply the length of the rod, which is the distance from A right up to B. That's the length of the rod, because this particle here is actually placed at the other end of the rod. Alright, so that distance there is D, which is simply the length of the rod, which is 2A. So we need to square it. So at the end of the day, we have 2m times 4a squared, which is going to give us 8ma squared. Alright, now what about the moment of inertia of the rod itself about the axis delta? Now we see that the axis delta is actually an axis that is perpendicular to the rod and passing through one of the ends. So we use our standard results. So let me just take the standard result. The moment of inertia of a rod whose mass is, let's say, capital M and length is capital L, so the length is capital L, about an axis passing through one of the ends and perpendicular to it, passing through one of the ends, is I equal to the mass times the length squared, then divided by 3. It's a standard result that we always use, and you can get it from the formula booklet, as well as you can prove it by integration. But here we are just supposed to use a standard result because we are not asked to prove it by integration, so we just use our standard result. So in this case, the mass of the rod is 4m. Okay, here is it, 4m. The length is 2a, so we have 2a all that squared, then divided by 3. So this is going to give us 4m divided by 3 times 4a squared, which will give us 16m a squared divided by 3. So you can conclude that the moment of inertia of this system about the axis delta is equal to, remember that we are summing 16ma squared on 3 to 8ma squared. So doing this clearly, you just get 40ma squared divided by 3 as required. So we are done with that. So if maybe we are asked to find the moment of, if maybe the axis was passing through the center of the rod, or maybe passing through a certain distance, maybe if it was the center of the rod, then we see that the moment of initial of our 2m here is going to be the mass times the distance from the particle to the center of the rod, which is a, because the rod is 2a. And then now this standard result here changes to ml squared on 12. Like I said, you can use the formula booklet. But as well, we need to know this standard result, because not all these standard results are found in the formula booklet. So we have to be very vigilant. Okay, so we are done with the first part of the equation. Now the second part of the equation tells us that the rod is released when AB is horizontal. So for this second case now, we draw our AB being horizontal. So we have our rod AB, which is horizontal. Okay, and then in fact, and then our axis automatically becomes vertical. So it's just to rotate this. So in this second case, we have something like this. We have the system is released, the axis is vertical, and then AB is horizontal. So we have A there, we have our mass there, and then we have B. So this is not needed. Then just try to rotate everything, and then I show you what is actually happening. So the mass is 2m, and then you have the NB as well. Now what happens is that the rod is horizontal, okay, and then this transforms to, so this transforms to this new shape. Now in this new shape, we have that the rod is released when AB is horizontal, and obviously AB makes an angle of theta with the horizontal. So we are not going to have something like this. This time around, the rod is going to move from that position, is going to move from this position maybe to sorry, I want to slant it. So it's going to move from this position, okay, to this other position. So something like this. Okay, so we have something like this, and then the horizontal is still there, the horizontal line is still there, and as well it moves with your mass, it moves with the mass, with the particle as well, which is 2m, it moves with it alongside. And then you also have your B. So AB now makes an angle of theta with the horizontal. So the horizontal now becomes the initial position of our rod. That's the horizontal. That's, we now call it the line of zero potential energy. So that's the horizontal. So let me put the axis now in bold. Okay, so we have something like that. Okay, now we need to indicate that angle, the angle that the rod makes with the horizontal. The angle is theta. So we clearly see that the angle is going to be this angle here, the angle between the horizontal and the new position of the rod itself in its new position. So that angle is theta. I'm going to indicate it there as well. So sorry for the delayance. Okay, So we have something like this. Let me put it in bold to indicate that that is actually the angle that the rod makes with. Alright, so the angle there is theta. Okay, so let's just indicate the theta and then we proceed. So like I said, the very first thing is to draw your diagram, because without the diagram you don't actually know what is happening. So there is the angle theta. Now after drawing the diagram, the next thing to do is that we apply the principle of conservation of mechanical energy, which says that mechanical energy is always conserved. In other words, the initial mechanical energy of a system is equal to the final mechanical energy, and mechanical energy is simply the sum of the kinetic and the potential energy of the system. So that's what we are going to apply. So after having this diagram as such, okay, we now have to apply that law of conservation of mechanical energy. So there are some concepts that I'm going to explain, so I plead of you to pay keen attention, because if you miss those explanations, then you always face difficulties with problems like this. You always be blocked at some certain points which you'll not be able to proceed. So pay keen attention to these explanations. Alright, so we are going to apply the principle of conservation of mechanical energy. Okay, it says that mechanical energy of the system initially is equal to mechanical energy of the system finally. Now, what does this mean? What's mechanical energy? Is a sum of the kinetic and the potential energy. So we have the initial kinetic energy plus the initial potential energy to be equal to the final kinetic energy plus the final potential energy. Now we need to look for these quantities and just replace them. Okay, now let us also label that horizontal dotted line there is the line of zero potential energy. So line of zero potential energy. So this is the line of zero potential energy, this line, because actually that was the initial position. Okay, alright, now having this in mind, it means that the initial kinetic energy of the system is equal to 0, because the system was at rest, because kinetic energy is half mv squared. So initial kinetic energy of the system is actually the sum of the initial kinetic energy of the rod with the initial kinetic energy of the particle. Okay, and then for potential energy we do same, but now since both the rod and the particle were stagnant, then their initial kinetic energy is 0 because they were not moving. Now what about the initial potential energy of the system? It's equal to 0 as well. Why? Because potential energy is mgh, and what is h? So let us define. Recall that so you should recall that potential energy is equal to, for a certain body, is the mass of the body times acceleration due to gravity times h. Now what is this h? Paying attention to this. This h is a distance of the center of mass of that particular body from the line of zero potential energy. I'm going to write it down so you get it clearly. So h is the distance of the center of mass, of a particular body from the line of zero potential energy. Okay, that is what h is. So you see that in the initial position there is no distance to that line of zero potential energy, because initially the horizontal axis here, which is AB, is simply the line of zero potential energy, so there is no distance to it. Okay, that's why the kinetic energy initial and that's why the potential energy initially is also zero. All right, now what about the kinetic energy finally? KE. So KE final becomes, remember that K is actually sorry for that, in fact let us see if this can enter here. Okay, now KE final. So the next concept that I'm going to explain is, remember that this body, let us also indicate how the body was moving, the direction of motion. Remember that it was rotating, so it was in undergoing rotational motion. Okay, that's, let's say, rotatory motion. So it is moving like this. Let me indicate it. So it's moving somehow like this. Okay, so somehow like this, that's the direction. So moving like that, we see that it is actually rotating, and we can say the angular velocity is omega, which is, we are going to see what it is actually. So we can say it is omega, that's the angular velocity, omega. Now, what is kinetic energy? Kinetic energy normally of a certain body is half times the mass of the body times the square of the speed of that body. Okay, so we have half times the mass of the body, but we know that since it was rotating, we need the angular speed, which is now omega arrow, then all squared. So this is going to give us half times m, then we can say m arrow squared omega squared. But if you look at m arrow squared, right, it is simply the moment of inertia of the given body. When I was calculating the moment of inertia of this particle here, whose mass was 2m, I said it is the product of the mass with the square of the distance between the mass and the axis. So it's the same concept here. So the mass times the square of the distance, because this arrow here is a distance from the mass itself to where the axis is. Okay, so this m arrow squared here simply defines the moment of inertia of that body. So we have I, then we multiply it with omega squared. But we should recall that omega is called the angular velocity, and it is actually the change in angular displacement. So omega is a change in angular displacement, which is equal to d theta by dt. So d theta by dt, we always say it is theta dot. So the dot there represents first derivative with respect to t. Okay, alright, so it means omega squared itself, you can say omega squared is simply equal to d theta by dt all squared, which is theta dot all squared. Alright, so our KE final, and so all we need to look for is our KE final and our KE initial. So this means that, so KE initial, so sorry about that, let's do this. So K initial plus K final equal to all of that, means that our K initial and our P initial are both 0, so 0 plus 0. So it means 0 plus 0, which is 0, is equal to our KE final, right, is simply this. Because normally to get a KE final, we take half times the moment of inertia of, because we need to take the KE final for the rod and the KE final for the particle. Okay, but since the rod and the particle make up the system, we can just use this formula directly by replacing I here with the moment of inertia of the system. They'll have the same angular velocity because they were attached together, they were moving together. Okay, so the angular velocity is the same. So this is just going to be I times the moment of inertia of the system, then times the angular velocity squared, theta by dt all squared, then plus, okay, don't get confused here. I'm using is and this. I could still, in fact, let me just try to explain so that you don't get confused if you're getting confused already. The final kinetic energy of the system, right, is equal to Ke final. So Ke final for the rod plus Ke final for the particle whose mass was m, or for the particle of mass m, let's just say particle is p. Okay, now we are going to have half times the moment of inertia of, because we are going to use this formula, so we have half times the moment. So we take for the rod is going to be the moment of inertia of the rod here, and omega squared will be the same as the omega squared of the particle because both of them were attached together. So we have this, but since omega squared, we have half omega squared is common, it means we can factor out the half omega squared from here, and then we are going to be left with this. When we factor it out from here, we are going to be left with IP. Okay, but we see that IR plus IP just gives us the moment of inertia of the system. Okay, that's why I've just replaced it with IS. Now omega squared is the theta by dt all squared, so there is no call for alarm. That's what I was trying to explain. Now what about the final potential energy of the system? The final potential energy of the system, so PE final, so the final potential energy of the system is equal to the potential energy final for the rod plus the potential energy final for the particle. Now we need to find those potential energies. Okay, so this is going to give us what's it going to be? Remember that potential energy is mgh. So for the rod is going to be the mass of the rod, which is 4m, then times g times h of the rod, then plus for the particle is going to be the mass of the particle, which is 2m times g times h of the particle. All we are left to do is, how do we find h of the rod and how do we find h of the particle? Let's go back to the diagram. We first of all get a definition of h. Our h is the distance of the center of mass of the particular body from the line of zero potential energy. So let us begin with finding h of the rod. So the first thing to do is we indicate the center of mass of the rod. It lies at the center. So I'm just going to indicate it with a dotted line. So the center of mass of this rod, maybe let's just pick that guy there. It lies there, you see. But what is h? H of the rod is the distance of the center of mass of the rod from the line of zero potential energy. So the distance from here to here, okay, this distance that I'm drawing is simply h of the rod. And since that is a vertical distance, and you clearly see that that distance is below the x-axis, it means it is going to be negative because it's kind of a vertical distance. The line of potential energy is like our x-axis, okay, and the distance is below the x-axis, so it's going to be negative. So that distance, first of all, is h arrow, which is the distance of the center of mass of our rod from the line of zero potential energy after the system is released and it is rotating about the vertical plane. Okay, now how do we get that distance? We know that if originally, okay, this is the center of the rod, because the center of mass of this rod will lie at the center. Okay, and lying at the center, it means that the distance from the axis to that center is simply the length of the rod divided by 2. Okay, so that's the length of the rod divided by 2, and since the rod has mass as 2a, it means that this small distance that I am putting there is simply a. Okay, so this distance here is a, and automatically it becomes the slanted distance that I represented here. So it means that if I come back here, it means this distance is also a. Alright, now that distance being a, we need to look for the opposite. We need to look for the adjacent, because it's a right angle triangle whose hypotenuse is a, whose opposite is h arrow. So let me just indicate that this is the distance. The distance from here to here is a. So that distance is a. So we are going to simply use the Pythagorean theorem. We use SOHCAHTOA. So if we use that, okay, we use that. Let's just find it here. If we use that, we are going to have that the sine of theta is equal to h arrow, which is the opposite to the angle, divided by the hypotenuse. It therefore means that our h of arrow is equal to a times sine theta. But remember that when we are going to be imputing it, it's going to be negative because it is a distance that is below the x-axis. Now that is h arrow. What about hp? So we have gotten h arrow already, remember. So we have gotten h arrow already. Now we need to get hp. hp is a distance of the center of mass of our particle p from the line of zero potential energy. And you know that since it is a point mass, it means it is simply this distance, the distance from here to here. So this distance, that's the distance we are talking about. So okay, that's the distance we are talking about. We are also going to use the Pythagorean theorem to get it. So this distance is hp, and using the Pythagorean theorem, we can clearly see that sine theta will give us hp divided by 2a, okay, where a is the length of the rod. So we see that sine theta as well, sine theta, if you consider now the big right angle triangle, meaning whose base, whose opposite to theta is this, it will be the opposite, which is hp. So let me specify that it is hp. So the opposite, which is this guy here, divided by the hypotenuse. But the hypotenuse is simply the length of the rod, which is AB, and the length of the rod was 2a. Okay, so we have hp divided by 2a. So what does this mean? It means that hp is equal to 2a sine theta. But remember that when we are going to be solving, we are going to give it a negative value because it is below the x-axis. So we just simply copy. You have a sine theta and the other one is 2a sine theta. So you have negative, remember, like I said, negative a sine theta, and then for hp it is negative 2a sine theta. That is it. Okay, this is what we have. So this therefore implies that we just need to fit what we have. So here becomes, now if you add these two, you're going to get let's see, negative 8mga sine theta. That's what you're going to get. Now we have the moment of inertia of the system. Let's see what we had initially. We had 40 on 3ma squared. We even proved it was a proof. So 40 on 3ma squared. So that's what we are going to replace. So this means that we just add 8mga sine theta on both sides of the equation. We equate it to half times is, which is 40 ma squared on 3. Then we multiply it with d theta by dt all squared. Then we start cancelling things. So from here, what are we going to get? We are going to get that we see that m cancels with the m. Now 2 goes here 20 times, goes there 20 times, so we remove this from here. Now our m has cancelled with the m here. Now our a, okay, here you're going to be left with 1a, so we can multiply both sides. In fact, 4 is going to go here 2 times and 4 is going to go here 5 times. Now we multiply both sides by 3. We have 5a d theta by dt all squared to be equal to 6g sine theta. So this is what we have. Let us verify if that was a proof that we are proving. So we are supposed to prove that, okay, 5a d theta by dt all squared is equal to 6g sine theta. Okay, so we are done with both proofs. Now the next part, I don't know if I'm going to proceed in this video. Maybe the video is already long, so I'm just going to explain it in another video. Okay, I'm just going to do that in another video. I'm going to upload 2 different videos, so I'll just continue my explanation, but for this third part, it's going to be in the next video. Okay.